welcome. Well, so I put this title, Understanding the Open Cluster Population, because as Alex said, I'm going to talk about the detection of open clusters, the characterization, as you have maybe guessed using machine learning techniques, but also what about the stars that we don't see that are part of the population of the clusters, and how can we include them in our studies. Okay, so first, if that works, which it doesn't, okay. So a little bit of introduction, so we are all on the same page. What is an open cluster, right? So an open clusters are gravitationally bound stellar groupings which are formed in the Milky Way disk from the same molecular cloud, so the same event. So they share same position, kinematics, same age, same initial chemical composition. And they are usually young structures because of the interactions that they are born in the disk, and the interactions, they don't survive that long, usually less than 1 gigayears. And in terms of Gaia data, which is what we're going to focus now, is the first time with Gaia. Well, with Gaia we have like astrometry and photometry for more than 1 billion stars, and it's the first time with Gaia that we can describe open clusters as in 9 dimensions, right? So in a high dimensional space. So we can describe them as stellar overdensities in this 6-dimensional space. We don't have radial velocities for all of the stars, so most of the times will be just defined in this 5-dimensional space. Plus, they follow an isochrone pattern in a color magnitude diagram, adding 3 more dimensions. So that is the definition of open cluster I will use for the rest of the talk. So Gaia, probably this slide is getting too old because people know already about this, but anyway, so Gaia is a space-based telescope, right? Its main mission is to map the Milky Way on a stellar basis. These are the different data releases that we have had from Gaia. We are currently here, say like, more than 1 billion sources with positions, parallaxes, which is a proxy for the distance, proper motions, and photometry, right? And we also have now 30 million sources with radial velocities. I put these numbers here. It's not that they are very, very relevant, but just to, despite the high number of numbers, we still have, Gaia is far from complete, and we're going to see that as well. Okay, so I said that we're going to talk about how we detected the open clusters. And this was the method that was motivated to find new structures, because as I said, it's the first time in Gaia that we have this wealth of data. So we need to find the structures in this homogeneous data set, right? So basically we wanted to find these structures, plus there was a scene with Gaia, so we had a catalog of open clusters previous to Gaia that counted with 3,000 objects or something like this. And with Gaia, we could only, when trying to characterize these objects, we could only detect around, less than half of them. So the other objects being too far to read for Gaia, or simply they were fake and not real objects. So we wanted to test how this affecting the population completeness by adding new clusters to the census. Okay, so now is where the machine learning comes in. So our methodology is based on 2 steps. In first step, as I said, these clusters can be defined as overdensities in the astrometric space. So we basically used unsupervised learning, so clustering algorithm, density-based clustering algorithm, to find these overdensities in the 5-dimensional space. Ideally, it would be the 6-dimensional space when we add the radial velocities, but because it's not a complete dimension, we let this out actually. And we find these overdensities using actually this dbScan algorithm. I'm going to talk about this later. And then we classify these overdensities into just random statistical overdensities or actual real open clusters. And we do this by training a neural network on well-known clusters, so the network can identify both cases in a color magnitude diagram. Okay, so what's the method? So we start from, I'm going to go through all the steps in detail, but just an overview here. We start from that Gaia data, we do a preprocessing step, which is usual in every machine learning methodology. Then we run the dbScan algorithm. I put this here as shift because we run the dbScan algorithm into a grid, and then we move the grid to count for clusters in the border. We'll see this. And that results in DB-scan clusters. That could be, as I said, real objects or random overdensities. Then with known clusters, non-characterized clusters, we train a neural network, and we finish with the new detected clusters. Okay, so step by step, the preprocessing. We do actually this grid. We are looking only in the galactic disk because it's where we expect to find more of the clusters. The catalogs, previous catalogs, like 95, 96% of the clusters were found in the galactic disk. So we focus only on this region. And then we divide this region into smaller areas because we are looking for overdensities. To look for overdensity, we need to define an average density. If we define an average density of the whole galactic disk, then the overdensities we'll find will be meaningless, basically. So what we do is focus on different smaller areas and then look for overdensities on these smaller areas. Well, the size of these areas is going to be optimized using simulated data, but I'm not going to go into that. Okay, so in each of these smaller areas, we run the DB-scan. Why did we choose the DB-scan? Because it's a density-based algorithm. It doesn't need to know the number of clusters we are looking for, so that is good for us. Can find arbitrarily shaped clusters, which is also good for us, so it can account for projection effects. And we all need to define two parameters, this epsilon value here and this minimum number of points here. I put here a two-dimensional sketch of a DB-scan. So basically, it will go point by point, define an epsilon neighborhood, and see how many minimum number of clusters can find in this epsilon neighborhood. If the threshold value that you set is reached, so it considers a cluster. Otherwise, it don't. By the way, the distance I'm going to use for the in between stars is going to be the Euclidean distance, normalized Euclidean distance in these 5 dimensions. And this is just a video of how DB-scan works. As I said, it goes point in point, define this neighborhood. If the minimum cluster number of stars is reached, then it's a cluster. Otherwise, it's not, like these empty black circles here.
Sorry. Oh, quick question. Is it okay to interrupt you with questions, or just sort of okay? So you mentioned that you normalize these things. So how exactly do you choose the normalization? It feels like that's important, right? Because it basically changes the weighting of relative importance of being close in the sky versus having relatively close proper motions, for example.
We just do the standard scaling thing. So convert all of them to have 0 mean and variance 1. So the relative importance is balanced. We did try to include different normalization schemes, but there was adding a lot of free parameters to be optimized, and it worked fine so far. Okay, so the L, which is the size of the little areas that we are running the DB-scan, plus the minimum number of points is going to be optimized using a simulation. So I will not talk about this now. I will talk about the determination of this epsilon value, which is automatically done in each area. And we use the fact that the stars within clusters, the stars in the cluster are closer to each other than random field stars, right? And you can see that in this plot here, this is the distance to each star to its 7th nearest neighbor. For the blue curve is the real data, and the orange curve is random reshuffling of the data, so removing all the substructor there, so there is no substructor, so all are field stars, right? And you can see that the stars belonging to this cluster actually are concentrated here in these small distances between the stars, which makes sense. So actually, we want to compute the epsilon as the value that isolates this blob here from the field. Okay, so we run all these in because we are running all these in the galactic disk, which are around hundreds of millions of stars. So we include like a big data framework. We do it on this Norton supercomputer in the Barcelona Supercomputing Center. It's not the details are not important. It's not the best computer in the world, but it was not anymore. But it's fine for us. But it is the most beautiful computer in the world, which is actually what we were looking for, because it's in a chapel and it's very nice. I suggest you can visit it if you have a chance. Anyway, so we run the DB-scan, the clustering method in parallel in all these regions. because I said we are running on up to G magnitude 17. It's couple hundred of million stars, sorry. But we will run, or we have actually run of deeper magnitudes because of the errors for the different data releases are better and better. And every time we run a deeper magnitude, we increase the number of stars by a factor of 2, basically. So that is the whole computation, but we randomly scan all in these small areas. That means like tens of millions of stars, depending of the limiting magnitude for our like bigger area. And compared to other algorithms looking on the for the same purpose, we can analyze much more stars than the other algorithms do, and that reduces the number of biases you introduce when tessellating the area or dividing the sky. Okay, so now we have the clusters, statistical clusters, may belong to real open clusters where you find an isochron in the color magnitude diagram, or you just is a random statistical cluster where there is no structure, no isochron pattern on the color magnitude diagram. And we want to distinguish between these two cases, and for that we use an neural network. This is just a Google image I took, like from the hand written digit recognition. But actually, the architecture that we use is very, very similar to this one. So we have a set of convolutional layers when it learns the structure of the correlations on the color magnitude diagram, and then they are flattened out and go for the classification layer. Actually, here we only have 2 outputs possible, which is cluster or not cluster. But yes, we use a very similar one. And the training set that we use to train the network is on well-characterized clusters, well-known clusters. So we have real cluster with Gaia measurements around 1,000 of them, all of them with the exhaustive membership study on them. And then we complement this data set with simulated data in a wide range of these parameters. Okay, so what about the results? This is not very relevant, but with DR2 we were able to find like around 600 clusters divided in different regions and in different qualities of cluster, let's say. And then in DR3 we were able to find like more or less the same amount. Yeah, so we were able to actually double the cluster census. And how does this affect into the completeness? So there is not a lot of studies on the completeness of the open cluster population. I think we should attempt to do some of these studies already, but in any case, this is an experiment we did with the recovery. So the clusters we could recover, the clusters that were known before Gaia, the ones that we could recover with our method. In green, you find the clusters that are fully recovered. In red, you find the clusters that we cannot detect at all. And in yellow, we have the clusters that we have detected using the clustering algorithm, but they didn't go through the photometric validation, let's say. So the neural network said it wasn't a cluster because it was not a defined main sequence, or it was too wide or something. And actually, Friedrich Anders, which is a collaborator of us, used this experiment to extrapolate the completeness results to all the whole cluster population. This is something very preliminary because it only relies on this particular detection method, so it's far from the final results. It might be a lower limit, but we find that for very, very young clusters, the completeness of the census is less than 50%. So still some work to be done there, and this goes up as the age increases, also because older clusters are usually found at higher galactic latitudes that we will see in a while, and then they are easier to detect. And that was based on DR2, sorry. And how has this improved in DR3? So not really, because, well, so if you see here, this is just up to 2 kiloparsecs from the sun. And how does this improve with DR3, with the number of clusters we have detected in DR3? So not really, because the crosses, black crosses are the new cluster in DR3, and you have this disk here around the sun where you cannot detect actually many clusters. So closer than 1 kiloparsec, we only detect like 3 or 4 of them, and closer to 2 kiloparsec, we detect also very, very few. And why is that? That is because of the improvements of DR3 data itself, which basically improves in the astrometry precision. These are the errors in proper motions as a function of parallax on the DR2 census and on the DR3, and we see that we have actually improved the precision, and that expands or that pushes the search further. And that is why we cannot improve the completeness in the local volume, let's say. Okay, so now we have a list with all the clusters, astrometric mean parameters, and now we want to compute some astrophysical parameters to enable further studies. How do we do that? So we want to compute age, distance, and line of sight distinctions, for instance, for these clusters. And how we compute that? Again, using a neural network, which is trained on well-characterized clusters. So in this case, we didn't have like 1,000 clusters to train on, but only around 200 or something. But what we do is, basically, we feed the network with the color magnitude diagram, plus some extra quantities that we think will help to the estimation. For instance, this S bright here is the slope between the turn-off and the red clamp. That's a proxy for the age. This MS45 here is the color at the end of the main sequence. That's a proxy for the extinction. And the mean parallax, which is a proxy for the distance. So we run all of these to find ages and distances, line of sight distinctions for the cluster population. And this is what we have. So actually, we have now around 2,000 open clusters with like astrophysical parameters, mean astrometric parameters, and this is the members of these clusters color-coded by age in an absolute magnitude color magnitude diagram, and we see that this more or less, this makes sense. So for all clusters, we can see the red clamp here, and for all clusters, we see like the main sequence here. So we are confident in these results. And now we can study like galactic structure with this in the different populations. So first thing we do is that we plot this galactocentric radius as a function of z. This is basically what we expect, also color-coded by the age. This is basically what we expect. So for the inner disk here, the clusters go to low z's, and this is because the galactic potential, which is heavy in the inner disk. And for the outer disk, the clusters go to higher z's. We can also see the flare here for young clusters, which is what we expect, right? What we didn't expect is these clusters here, high galactic latitude clusters that are not expected to be there. And all of them are old clusters, right? So what makes these clusters special to be able to survive to these galactic latitudes or why can we find young clusters on these high galactic latitudes? This is something we are working on it. So there are a few proposals to study this, but I cannot say anything else about this now because we don't have the data yet. Something that we can also do is to study the symmetric components of the galactic disk using also this population. We see that if we plot this XY surface plot in different age bins for the very, very young clusters, we see that the distribution of this is highly structured. So we actually see structure over densities that may correspond to the galactic spiral arms or may be related to galactic spiral arms. Basically, we think that the stars are forming the galactic spiral arms, so we can have an overdensity of these young objects where they are formed, which are the galactic spiral arms. And then as you go older and older, this substructure is dispersed and removed basically completely for very old clusters. So now we focus on this, and we try to characterize these overdensities and relate them to spiral arms, actually. So what we do is we plot the very, very young clusters, meaning 30 million years or younger. In this plot, galactic azimuth and galactocentric radius, and we see that still find these overdensities. We run a Gaussian mixture model to find the meaningful overdensities here. Actually, this Gaussian mixture model knows nothing about the distribution here. We run it on different setups, on different configurations, and we can always find the 4 more meaningful overdensities being these 4. So that means that they are stable against the method. And then we feed we fit a linear fit here that belongs to the log periodic spiral arms, so we can describe the spiral arms or get their parameters as a function of these clusters. And this is what we did actually. So basically what we did is we have the Young clusters plus the traditional tracers for the spiral arms, which are the high mass star-forming regions. We see that they were compatible, so we add them together and we have the description of the spiral arms on the solar neighborhood. The advantage of using these two different tracers is to reduce the statistical errors of the fit, of course, but then we don't have data for high mass star-forming regions in the 4 galactic quadrant, so we can expand the azimuthal coverage of these arms on this region. Okay, so now we have the description of the arms. We have like the clusters that belong to each arm. These clusters have ages, among other astrophysical parameters, and they also have radial velocity, some of them. So we want to study the evolution of these clusters. Basically what we do, so I'm going to have this GIF running here. Yeah. Basically, we want to study the evolution of these spiral arms traced by the clusters. Basically what we do is, so imagine this cross is a cluster related to this arm. We integrate backwards its orbit following a Milky Way potential. Then at this point, we don't consider this point to be a cluster anymore. We consider this point to be a location of the spiral arm when the cluster was born. And then we evolve the arm using an arm-like rotation, so circular rotation, with a certain pattern speed, which is what we want to guess. Then we iterate over if the pattern speed is correct, like in this case. So the projected arm will overlap with the present day arm, otherwise it will be short here or will be further away. So we iterate over different realizations of pattern speed to guess the optimal one, and we repeat this procedure to account for errors, and this is what we get. So we have defined 4 different spiral arms, Perseus, Local, Sagittarius, and Scutum, and we run this methodology here, and we find that each of them have a different pattern speed, which is actually decreasing when the galactosectic radius increase, so decreasing with the rotation curve, and that tells us, or this favors the classical density waves as the main mechanism to form spiral arms, and favor transient spiral arms that form and dissolve along the time. Okay, so now we're going to move to the selection function. So basically, okay, so what do we need to get a more complete cluster catalog? So we want to keep improving the open cluster catalog. Basically, okay, we can do more homogeneous membership determinations, more homogeneous astrophysical parameter determinations, but also we can add some other astrophysical parameters to enable further studies. And one of these parameters would be the masses. So for instance, if we want to compute ages on these 2 cases, we will know that this is old, we know that this is young, because we are only focusing on the shape of the isochron in this case. But if we want to compute masses, we will have to focus on the distribution of the stars along these isochrons. And we see that this is not what we would expect, where the peak here, or the maximum density is here, while we would expect the maximum density to be towards fainter magnitudes, and same here. So we have to correct for that using the selection function of these members. And because this is a difficult case, I put here an example of an easier case that is basically the same. So this is the white dwarf population in Gaia. Basically, this is what we will retrieve, doing a set of cuts in color, distances of parallax, and magnitudes that will retrieve, and we will retrieve the white dwarf population, but same. So the density, maximum density in this case is here, where we will expect maximum density to be toward fainter magnitudes, and this is what we get here. So every one of these cuts introduce a selection effect that can be accounted for. In this case, it's very simple, so we could analytically estimate the selection function, and basically we use the observed population corrected by the selection function, and we see what we should have. And what is this selection function. So in our case, so we have the data, in this case collected by Gaia. This will lead to survey catalog that may be dependent on the detection efficiency of our telescope in this case, or the angular resolution, or the different wavelengths, or whatever. And then we do some kind of pre-processing step. This also introduces further selection effects, and then we have the parent catalog selection function, right? And that is what we want to describe in this case now. And we have two ways of describing this. First approach is forward modeling, so it's knowing all the procedures that are included from the data taken to the generation of the catalog. So we need to know every step that we have taken, and then we can, if we understand those, we can provide the selection function. But that is, yeah. So the scanning law, how Gaia scans the sky, the ability to convert these observations into detections, then how we get rid of spurious or bad detections, or the decisions taken in the data processing. This is something we are working on, preliminary, so I'm not focusing on this now. And then the other thing is to compare our catalog with a ground truth, or a more complete catalog, right? And if we know the ground truth, we know what stars we are taking. If we compare them, we know the completeness of our catalog. And this is basically the approach taken in this empirical model, where we compare to a ground truth. In this case, is a deeper photometric catalog, decals in this case here. So this will be the density, source density in decals. This will be the source density in Gaia. When we divide one from each other, we see that basically we can recover everything up to the Gaia limiting magnitude, basically. So we want to characterize this to get the selection function of Gaia in this way. And we see basically that the source density of decaps, that we consider is the true source density, is a very good proxy for the completeness. So for sparse regions, we see that basically the completeness of Gaia drops at the Gaia limiting magnitude. And now, as we go to denser and denser regions, the completeness of Gaia drops a bit earlier, and here it drops way earlier, also losing some stars here. And this is what we want to characterize. The thing is that for decaps, we don't have an homogeneous survey in the whole sky. So we want to characterize this based on data that we can get from Gaia only. And this is this parameter here that after some trial and error, we found that the magnitude of the sources with less than 10 observations, so Gaia, to include a source into the catalog, we need at least 5 observations. A lot of Gaia sources have more than 100 observations, for instance. But this will be, having 5 observations will be the limit. So when we see the sources that have less than 10 observations, we are actually reaching on the limits of the observability by Gaia. And we saw that computing the magnitude for these sources is a good proxy for the completeness, actually, we saw earlier. And this, I will save you the details here, but basically we have this magnitude M10 map, and as a function of sky position, as a function of magnitude, we run more or less complex statistical model, and we get the selection function for Gaia sources, for Gaia data as a function of sky position and magnitude. We can go into the details, but it's not necessary. We have put everything into a Python installable package that you can query, and there is a lot of tutorials and documentations, and basically you will finish with this, where you can actually see how complete is Gaia. First thing you notice is the Gaia scanning law. So in sky locations where Gaia has scanned more times, you are more complete because Gaia has gone through there more times. Where do you have a lot of, the true source density is very, very high, as in the galactic center, you have very low completeness. Same for the Magellanic clouds. And actually you can see these dots here is not problem of the screen or anything, but it's actually the globular clusters where in the center of the globular clusters, the completeness drop a lot. And you can actually detect them using the selection function. Okay, so I think I'll finish here. So this is my summary. I just explained a data mining method to blindly search for open clusters. We are more or less successful in the sense of the number of clusters we have detected. Also, I have described how we compute the astrophysical parameters for this, and then we use them for an actual science case, which is the description and evolution of the spiral arms on the solar neighborhood, and we find that the description of the clusters of the spiral arms disfavor classical density waves, finding a transit behavior of the arms. And then at the end, I show how we develop an estimation of the selection function for the Gaia catalog, which is necessary to extract meaningful conclusions. And I will finish here. I'll take any questions. Thank you very much.
I had a question about the last one. If I understood your model correctly, once you have a certain minimum number of observations, all that matters is the median magnitude, right?
Mm-hmm.
But I would have thought, does that mean that Gaia doesn't do any kind of stacking in its analysis, right? Because you would think, okay, if you see a source that's too dim to ever be individually observable, but you see it in the same place lots and lots of times, you should eventually be able to somehow stack that together and get a stronger source, right? But that doesn't seem to happen.
No, I don't think so. Do you know if they stack things together? No.
All the processing's done on board.
Yeah.
So.
I see. So if you don't see it individually, you don't see it at all.
Yeah.
Got it.
There's limits on the source density. You can speak more about that, I suppose. Yeah.
So actually, all of these will be, not the stacking thing, but all of knowing all of these processes will be so how many times we can observe the source, how many times this is becoming a successful observation, then how many times we don't drop these observations because of, I don't know. And that is something we are working on, but we don't fully understand what's happening. So actually, with this map here, we have, so this was the empirical version, right? So computing the differences between a ground truth and Gaia. Like for the forward modeling, we have a similar map, but it completely overestimates the completeness, and that is basically because we don't fully understand what's going on. We can understand some things, but not all of it, and we're still working on it. Yes, and that is why I didn't explain.
So how does binarity of stars affect this clustering algorithm and also the analysis on stellar properties and color magnitude diagrams?
Yeah. Well, so we didn't focus on the binarities. We just basically forget about this.
Assuming that they're all single stars, you exclude all the binaries. Or what is the approach that you take?
Actually, we didn't take any approach. We just take the data from Gaia and do the clustering. And then if there's binaries or not, we just take the mean astrometrical parameters. So if they are close together following these metrics I showed, we consider them a cluster. And then in the color magnitude diagram, the binaries do not affect much because of the way we normalize the color magnitude diagram. So unresolved binaries, for instance, that will show a secondary sequence, that is basically gone because of the way we normalize the color magnitude diagram. So we only focus on the isochrone shape. Same for the blue stragglers, for instance. And that we do this to account for, because for instance, for the blue stragglers, if we didn't normalize this way, we will find a very, very young age for a cluster, which is not that young, right? Because we'll have the whole sequence following the blue straggler sequence as well. For the binaries, it's not that direct, the comparison, but this is the same approach, right? Yes, and we do that to account for this, but also to account for certain level of contamination. So basically, if we have the color magnitude diagram here, you see, as I see, the blue stragglers or some undefined binaries here. So we basically, for the normalization, because this is much populated, so when we normalize, basically, this is not seen by the network. Right? What I was going to say? Yes, and so we do this because to take into account some kind of contamination. So if we find this, but the clustering algorithm is not perfect, and we find some members here which are actually not belonging to the cluster, and we send this straightforward to the network, the network will say this is not a cluster because it has like a good, well-defined main sequence, but then you have some random stars here, so not a cluster. That is why we normalize this to just focus on the meaningful features, actually. We try different kind of normalizations, and that was what worked. Otherwise, it will be like way too many false positives. Mm-hmm.
Each cluster will have some small intrinsic velocity, radial velocity variations, which tells you a bit about that cluster's properties and history and things like that. You don't have radial velocities for most things, but you do have proper motions for everything. So have you looked to see what the unprojected spread of proper motions is for every single cluster as like a function of age or luminosity of the cluster or something like that, to tell you about how the systems are relaxing through the disk?
Not myself. I think there is one study on that by Tristan, actually, but I am not. I didn't participate in the study. I don't know. So I didn't do it, and I can check if that paper actually focuses on that or not, because it's describing basically the proper motion distribution in the clusters, right? Yeah, but I am not fully aware of what they do in the paper.
Mm-hmm. Maybe related to that, right? There's the issue that, I mean, your clustering algorithm sort of focuses on figuring out, what constitutes a cluster, right? Or whether something is a cluster, right? But once you've identified a cluster, there's a separate question of which things are really cluster members and which aren't, and therefore what are the cluster properties such as velocity dispersion and so on. And for that, it's not clear to me that the initial clustering algorithm is actually the right approach, because you might, at least I would consider sort of some probabilistic assignment saying that, this thing which I identified as a cluster member could just be by luck in the right place and with the right velocity, and this other thing which I didn't call a cluster member because it was a little bit off of the main sequence or whatever, actually is a member of the cluster. It just is a blue straggler or something weird happened to it, but it actually should be included if I want to understand the cluster properties and history. So do you do anything like that where you do some afterwards some probabilistic thing?
Yeah, so this is actually done in 2 steps. What I show now is the step I've been more involved in, which is the detection of the cluster. So basically what we do is spot the cluster locations. And then we have separate kind of methods, separate kind of algorithms that go to these cluster locations and do this probabilistic analysis. Actually, this with same unsupervised membership, so it only knows the mean position of the cluster, and then it finds members, but then it's refined with some other supervised methods, yes. I didn't explain that part, sorry.
You know how you use open clusters as traces to model the structure of the arms? Why does that exactly disfavor spiral density waves?
Yeah, so for spiral density wave, basically what you will have like these strong spiral arms, and they move like a solid rigid, right? And they all move like a pattern, so they all move like the same way. That will be actually this result here, which I also omitted in the talk. But basically, having a global pattern speed will be an indication of having this solid rigid structure moving coherently on the galactic disk. While we don't find this, we find that every spiral arm has its own pattern speed, and it's actually moving, like co-rotating basically with the disk at every radius. And what that means is that the spiral arms, the stars form gravitational instabilities or whatever, and then the spiral arms form, and then they disappear because of the differential rotation of the galactic disk. And so for this density wave, you will have this solid rigid that will be like a long-lived structure, so it will live for giga-years. I'm naturally not sure, but that's the order. And then for this one, there will be short-lived, recurring, on the order of 100 or 150 million years. And that is why, you can distinguish. We have other clues I didn't explain. So We have independent means of also tracing this by comparing with other tracers, checking the age of the distribution of the age of the structures across the spiral arm. We have other means for doing that, which I didn't include in the talk. But yes, that would be the main thing. I think it was.
Sorry, I'm a bit confused about your argument there, because aren't you assuming that the pattern speed is fixed in your analysis in the first place? Because in the density wave picture, the same stars don't live in the spiral arm, they move in and out of the spiral arm. But the way that you've calculated the speed in the first place, you assume that those stars were in the arm when the arm was on the other side of the galaxy.
Well, actually, I simplified this a bit. Where is my thing? Okay. We did use this and test this on different scenarios. Okay. So basically, this is what we test, right? So basically, we simulate the spiral arm, we rotate it backwards with a set of pattern speed, and in every time step, we simulate cluster-like objects with cluster-like velocities and everything, and then we evolve to present day. And this will be like the kind of situation we have now, right? So for our method, so basically we test two cases. First case is, can we distinguish the pattern speed from the rotation curve? Because if you have the same objects, you integrate backwards and then you project the arm forward, then you're measuring the rotation curve, right? So we did that, and with the setup of the toy simulation that I just explained, okay, if we have, on the first case here, we trace the present day spiral arms and their evolution with different tracers, meaning on this case we have high mass transforming regions to trace the zero age spiral arm, which are very, very young structures, and then we use clusters of different ages to trace their evolution. We can always recover the pattern speed. If we don't have these different traces, or consider the high mass transforming region are not young enough, I don't know, or the age of the cluster are not well constrained enough, I don't know, this is not fully independent tracers. If we trace the spiral arms with the youngest population that we know, the larger the age difference between the zero-age spiral arms and the evolution, the ones tracing the evolution, the larger the age difference, the closer it gets to the true value with the true value of the pattern speed. That's one case. Second case is that is if we have one pattern speed. What if we have different pattern speeds? Can we distinguish from each other? And the answer is yes. So we did this with the same setup with two different pattern speeds. Okay, these were extreme cases, but actually is what we see in the Perseus arm, more or less like 20, in the Scutum arm, more or less like more than 40, 45. And we can actually distinguish, okay, maybe we don't recover the exact value or within 2 sigma or something, but we distinguish between this and this. And that is what we did. And that is why we have here different age intervals to see how these behave on the different scenarios that we have in the toy model. And actually we see that these are stable within the different age intervals, within errors, and actually different from each other with errors as well. And that is what made us believe that we were on the right track. Also, as I said, okay, I can show some more things. Do we have? So all the clues is like if you have a density wave, represented here by the gray dots, the density wave moves at its own pattern speed. The stellar population moves at the galactic rotation curve. So as you said, the stars will travel through or across the spiral arm, right? So you will have this age gradient across this spiral arm. And actually this was studied by Dobbs and Pringle. This is density wave scenario. This is bar-induced spiral arms, flocculent galaxy, and merger-induced spiral arms. And the age of these cluster structures across these spiral arms, you can see here the gradient that will belong to this case. We have density wave. You can also see gradient here, and you don't see gradient in the flocculent or in the merger-induced spiral arms, right? And this is what we find on our cluster sample. So for the local arm, it is clear that you cannot see a gradient. That is corrected also for the completeness, more or less. So you cannot see a gradient here, but you cannot see gradient here either or here. Plus, if you consider this is the rotation radius, the gradient should be in opposite directions and stronger as the farther you go from the rotation radius. And we cannot see this imprint on the spiral arm. So that is what it makes us believe that it may not be like a grand design density wave spiral. Yeah. No.
A dumb question. Which is just your open cluster with your age. You had the plot with the T on it. Yeah, I think that one.
Which one, sorry?
You had the color bar showing the age of stars in an open cluster.
This one?
Yeah, so I was just confused by this plot because you started your talk saying open clusters are all born at the same time, all the stars are the same age.
Well, within an open cluster. So these are... No. These are the whole population. Yeah. So I just plot here the members of each open cluster for all of the open clusters.
Second dumb question, if I can, is why is DR4 the final data release?
Why is DR4 the final data release?
Yeah. Is there no more observations after that? Does it get shut down?
Yeah, there's more observations. I mean, no, the DR4 will include everything. I don't know if there will be a final release or not. Yeah? I mean, it's run out of gas.
It's already finished.
No, not now, but it will run out of fuel.
When does it run out of gas?
I think 2 years, 3 years from now, something like this.
Can't send up someone just to go and refuel.
Are you volunteering? No.
So the mission was initially for 5 years. There was already known that the fuel would be for 10 years, something like this. But they need to get from 5 to 10. They need to get like sequential approvals of the mission length. I don't know what the status actually, but we'll probably go to 10 years.
The most expensive thing after that is tracking Gaia's position from the ground with radio telescopes, which is expensive.
So if you did refuel it, would it be useful to run for another 10 years?
I don't know. The thing is that, so I think what is more useful is not, I mean, running Gaia for 20 years would be okay, but would be more useful having like a second Gaia, for instance. Like with the Parcos and Gaia that was the, it was in different times, right? Not a continuous mission for that long, because the improvements actually, so for DR2 that was 2 years something, I think, to DR3, the improvements that was 3 years, the improvements were quite good, but then it like kind of stabilized on the positions. While if you have like another Gaia sometime in the future, that will help a lot. And if it can be in a different wavelength, it will, like more or less in a different wavelength, that will also help a lot. Yes.
Hang out for you.
Thank you.